Hello friends, welcome back to my channel. This is Chandu Prashant. So very good evening all of you. So today our topic is an introduction to low power VLSI and its design techniques. Right? So let us discuss about what is the need for low power VLSI. After that we will going to discuss about what are the design methodologies are there and what are the different types of power dissipations are there. So everything we'll go to discuss, right? So let's see here. Why low power? So there are some reasons why we require low power. And first reason is power efficiency. So it reduces energy consumption in battery operated devices like smartphones, tablets, laptops, etc. Nowadays most of the devices are battery operated devices. That's why the low power is required. And second reason is heat reduction. It minimizes heat dissipation and improving device reliability. It is another reason. And the third reason is enhanced performance. And low power consumption allows higher clock speeds without excessive heat. It is a third reason why we require low power. And fourth reason is battery life improvement. It can essential for portable and embedded system to extend battery duration. So and the next reason is cost reduction. And it reduces cooling requirements and power supply cost. And next one is scalability. It helps in designing power efficient high density ICs for future semiconductor nodes. So ICs in the sense integrated circuits. And next one is reliability. And low power nodes reduces this electron migration effect and aging effects. And it can improve the reliability of the device. And next one is thermal management. So it eases sparking and cooling system design and reducing overall complexity. So and we can also say it can also reduce the sparking and cooling cost. So for all these reasons we required low power. And let us discuss about what are the different sources of power dissipation that we have. And power dissipation, the rate at which energy drawn from the power supply, we can call it as power dissipation. We have two types of power dissipations: static power dissipation and dynamic power dissipation. Static power dissipation. If inputs and outputs don't change, we can call it as static power. If inputs and outputs are changed, we can call it as dynamic power. Simply. So if you can see here, static power dissipation. If inputs and outputs don't change, both pull up and pull down devices are simultaneously on for low output level, causing DC to flow. And dynamic power dissipation. So it is due to change in input and output voltage levels. So we can say this dynamic power dissipation occurs when these circuits are working in condition or working condition are in active. We can say this. In this situation, the dynamic power dissipation will going to occur. Okay. These are the sources of power dissipation mainly. And we can see the further classification. What are the different types of dynamic power dissipations we have? We have mainly three types: switching power dissipation, short circuit power dissipation, and glitching power dissipation. Let us discuss about switching power dissipation. The power required to charge and discharge the output capacitance is called as switching power dissipation. So if we can see this formula, the switching power dissipation is directly proportional to load capacitance, square of the supply voltage, and frequency. Right? So see this diagram. It is a conventional CMOS network. It consists of pull-up network which lies between VDD to output and pull-down network which lies between this output to ground. So and here there are two scenarios: charging the current and discharging the current. If you can see here, the load capacitance charges and discharges as the output changes from low to high and high to low level. So in this way it can able to charge the capacitance and discharge the capacitance. So there is a switching activity: charging, discharging, discharging, etc. Okay. So it is about switching power dissipation. And the next one is short circuit power dissipation. Okay. It is mainly due to finite rise time and fall time at the input of CMOS logic levels. Okay. Here And so in this condition, both PMOS and NMOS are in on condition. Okay, if you can say CMOS is a combination of complementary metal oxide semiconductor is a combination of both PMOS and NMOS, right? So here both PMOS and NMOS transistors are simultaneously on. Okay, for some duration. So it is shorting the power supply line to the ground, and it leads to the current flow between supply to the ground. So you can see this diagram. It is a conventional CMOS inverter diagram. Okay, so it is a formula. So from this formula we can say that its short circuit power dissipation is directly proportional to rise time and fall time, and it is directly proportional to supply voltage, and we can also derive the conclusion that it can directly proportional to the frequency also. Okay, so it is about short circuit power dissipation in this either PMOS or NMOS are on, okay, at some durations simultaneously. And the next one is the glitching power dissipation. So it is mainly due to finite delays in the gates. If you can see here, glitches occur because input signals to particular logic block arrive at different times. Input signals arrives at different times, causing number of intermediate transitions. Okay, causing number of intermediate transitions to occur before the output of logic block stabilizes. These transitions are result in glitching power dissipation. These transitions are nothing but glitches. These glitches are rise to glitching power dissipation. You can say this. It is about glitching power dissipation. Let us see some example so we can understand this glitching power dissipation very clearly. So see this example. So I have a circuit which is constructed with two NOR gates. Okay, two NOR gates, simply one simple circuit. So initially I am considering the input 101, so that I am getting the output is logic 0. So if I can switch from the input 101 to 000, so I can get the output is 0. So ideally for 0 gate delay, if input is changes from 101 to 001, output remains at 0 logic level. If I consider unit gate delay, so the output is delay, and as a result output is switching to logic 1. This time initially the output is 0. This time if we consider the delay, so the output switches to logic 1 for 1 gate delay duration. Initially it is 0. So if I consider this input, I am getting the output is logic 1. Okay, you can so observe this diagram. So O1 output, so initially it changes from 0 to 1. So if there is a glitch due to this finite delay or finite glitch, it can occur glitching power dissipation circuit. And see here initially it is 0 to 1. So see here it is 0 to 1 and again 1 to 0. Due to this delay, it can cause glitch in the circuit. So this glitch will lead to glitching power dissipation. Okay, so whenever you are transit from 101 input to 000, so the output will going to change, and this particular glitch will causing the glitching power dissipation. So generally the cascaded circuits will exhibit this glitching power dissipation. So if you can cascade any circuits, it leads to glitching power dissipation. So if I want to avoid glitching power dissipation, what I have to do? So the glitching power dissipation can be minimized by realizing a circuit by balancing the delays in the circuit. We have to balance the delays in the circuits, then we can able to reduce the glitching power. Generally, this glitching power dissipation occurs in most of the cases in cascaded circuits only. Okay, so it is all about dynamic power dissipation types. Let us discuss about static power. Okay, the static power dissipation are mainly occurs because of leakage currents. So see here it is a MOSFET device, consists of source, gate, drain and body terminals, and all the 7 currents, leakage currents are described in this diagram. So first one is I1. A reverse bias PN junction diode leakage current, and the second one I2 band to band tunneling current, I3 subthreshold leakage current, I4 gate offset tunneling current, I5 gate current due to hot carrier injection, I6 channel punch through, I7 gate induced drain leakage current. So all these are the various leakage currents occurring in this particular MOSFET device. Okay. And leakage currents is mainly of the four types, mainly subthreshold leakage, gate leakage, gate induced drain leakage, and junction leakage. And we are not going in depth of all these leakage currents, so we have to know these many leakage currents are there. So the static power occurs mainly because of these leakage currents. So all these are the various leakage currents so are there in. Okay. And leakage power is an important issue when compared to dynamic power. Why? Because leakage current increases significantly. So leakage current increases at a faster rate than dynamic power. We can see this from this diagram. So leakage power is more important. It can increases rapidly with the the dynamic power. That's why there is an immediate requirement to reduce the leakage power in the devices. Okay, to enhance the performance and reliability of the device, we have to reduce the leakage power in the devices. And second part of our discussion is techniques to reduce the power or design methodologies to reduce the power. Okay, so various techniques are exists both at the device level and architecture level. So we shall discuss the both techniques for reducing dynamic power and for reducing static power. Okay. So dynamic power reducing techniques. Okay. So we have the switching power dissipation, glitching power dissipation, short circuit power dissipation, and we can say that dynamic power is directly proportional to this alpha C VDD square F. Okay. So where alpha is the activity factor, C is the load capacitance, VDD is the supply voltage, and F is the frequency. We can say this dynamic power dissipation is directly proportional to this all these factors. So the possible strategies for reducing the power is, if we can reduce the alpha, we can reduce the power. If we can reduce the capacitance, reduce the dynamic power. Reducing the VDD reduces dynamic power. Reducing the frequency, so we can reduce the dynamic power. So all these are different possible strategies and techniques like clock gating, sleep mode transistors. And for reducing the C, we have to use small transistors and short wires. And reduces the VDD, we have to reduce the supply voltage. If we can reduce the supply voltage, delay also increases. Again, it's a trade-off. We have to remember that. So again, it is an issue. Reduce the frequency. If you want to reduce the frequency, we can reduce the clock frequency to the extent possible. So all these are some of the techniques to reduce the dynamic power. And reducing static power. So for reducing static power or leakage power, so we have some more techniques like selectively use ratioed circuits. Ratioed circuits are nothing but a conventional CMOS circuits all. And another techniques like by using stacked devices and body bias and reducing the temperatures. By using all these methods, we can reduce the static power. In this way, we can reduce the static power and dynamic power. So let us discuss about all these techniques one by one elaborately. So let's see the first technique, that is clock gating. So this clock gating technique is used to reduce the dynamic power dissipation. And the basic idea of clock gating is we have to switch off the clock signal from the functional modules that are inactive. So if there are inactive modules are there, for that modules we have to switch off the clock signal so that we can minimize the dynamic power dissipation. So the clock signal is responsible for the signal activities. So there are some drawbacks with clock gating. That is, we have to use some additional hardware. Okay, and also another drawback is a clock signal might get delayed due to increase in the critical path. It is another drawback with the clock gating. So even though some drawbacks are there, So it can reduce the dynamic power dissipation. Okay, let us see this diagram. So it is a resistor and functional units. For that I am attaching the simple OR gate, which consists of this clock and the disable signals, and the gate selectively disables the clock and this disable signal, and we need a logic to generate the disable signal, and this added circuit. So this particular circuit will consume the power, and also it increases the area also. And another drawback with adding this circuit is, so OR gate delay gets added to critical path. That means delay also increases. Delay or skew also increases. So the possible strategy for managing this skew or delay is, we have to replace these OR gate with a buffer in a clock distribution T, so that we can minimize the delay, and also we can able to reduce the dynamic power dissipation. Okay. And next most important thing is the supply voltage reduction. So it is another technique to reduce the dynamic power dissipation. Why? Because so dynamic power is directly proportional to square of the supply voltage. That means reduction of supply voltage is most significant phenomena. Okay. So in supply voltage reduction, generally we can follow two approaches, that is static approach and second one is dynamic approach. In static approach, distribution of power supply voltages is fixed every year among various functional blocks. Whereas in dynamic approach, power supply voltage is changed as required. Okay, there are two approaches, static approach and dynamic approach. Let's see one by one. First one is static approach. So see this diagram. So here there are three functional blocks. I want this central block. To be first, but remaining two blocks I don't mind. If they are running slower also I don't mind. So I can use a pair of supply voltages. Rails. One for low supply voltage and another for high supply voltage. So these are for low supply and these two supply rails are for high supply voltage. Okay. Blocks which are run to be very faster are fit to high supply voltage. See this orange color. The block which is supposed to run faster is fed with high supply voltage, and blocks which are run slower fed with low supply voltages. Okay, so it is a static approach. But the major issue with the static approach is routing is complex here. Power routing is complex. Okay, so for that we need to take a special care for interface between the power domains. So it is one drawback with static approach. Okay, see the dynamic approach. Okay, nowadays modern processors have several modes. We can see, for example, high performance mode. Okay, it has high VDD and high frequency, and power saving mode, another mode, that is low VDD and low frequency. This approach provides flexibility and does not limit performance penalty of transition between power states can be high. So dynamic approach can require additional logic that's all required. So let us see this voltage islands, this orange color and blue color. So this orange color may be VDD high, for suppose VDD high. This blue color will be VDD low. Okay, it is a standard cell kind of placement. The cells are arranged in rows like this. So all these are cells are arranged in rows. This orange indicates VDD high. This blue color indicates VDD low. The cells which are supposed to be high performance cells are placed in orange rows. That means which is fed to high supply voltage. The cells which are supposed to low performance placed in blue color rows. That means which are fed to low supply voltages. So it is a standard cell kind of arrangement. Okay, so say it is in a voltage island. So in this way we can able to reduce this dynamic power dissipation. So that means we can able to reduce the supply voltage. So further it can reduce the dynamic power dissipation, right? And so there is one more important concept here, that is level converter. Okay, so level converter is one type of a circuit. Whenever you are driving a circuit with low supply voltage to high supply voltage or high supply voltage to low supply voltage, we require a level converter. It will convert from high supply to low supply or low supply to high supply. For that we require one level converter circuit. So it is an simple CMOS inverter. Level converter circuits are formed by cascading this CMOS inverter. It is one inverter, so it is another inverter. We have to cascade the inverters. Alright. So it is a low to high level converter. First one. It is a high to low level converter. So low to high level converter introduces a more delay because it has two supplies. See here, VDD high and VDD low. Whereas a high to low level converter will consists of only one supply, that is VDD high. So in both low to high level converter, so high to low to high level converter and high to low level converter, in both these we have to cascade these CMOS inverters. Okay, so it is one of the circuit. So it is one of circuits are driving with low supply voltage to high supply voltage or high supply voltage to low supply voltage, vice versa. Okay, and third technique is dynamic frequency and voltage scale. Okay, energy drawn from the power supply can be reduced by the following methods. First one is dynamic frequency scaling. Dynamic frequency scaling. And second one is dynamic voltage along with frequency scaling. So dynamic frequency scaling, here we have to lower the frequency with varying load. So and we have to keep supply voltages constant. So okay, in dynamic voltage and frequency scaling, we have to reduce the frequency. Also we have to reduce the supply voltage. In dynamic frequency scaling, we have to reduce the frequency and keeping the supply voltage constant. In dynamic voltage and frequency scaling, we have to reduce both the frequency as well as supply voltage. It is another technique to reduce the dynamic power dissipation. Okay. So and static power reduction techniques. Up to now we have discussed about dynamic power dissipation techniques, how to reduce the dynamic power. So now we have to discuss about static power reduction techniques or leakage power reduction techniques. The various approaches to reduce the static power are reduce the leakage by stacking the transistors and dual VTH partitioning. VTH in the sense threshold voltage and variable threshold. These are the three methods. By using these three methods, we can able to reduce this static power dissipation. Okay, let us see one by one. First one is using transistor stacking of transistor. Okay, stacking of transistors. So see here, all the transistors are connected in series. So all these are the NMOS transistors are connected in series. Transistor stacks that are naturally appears in a design help in reducing the leakage current. So stack in the sense several transistors are connected in series, so that effective leakage current also decreases. So see here, assume the gate voltage is 0 for all these transistors. Okay, the VGS of all these transistors is negative. Moreover, drain to source potential is also reduced. Okay, we have to stack these transistors so that we can able to reduce this leakage current. Okay, it is one of the method to reduce the static power dissipation. And the second technique is to reduce static power or leakage power is dual VTH partitioning. Okay, dual threshold partitioning. The basic concept. There are two types of transistors, low VTH transistors and high VTH transistors. Low VTH is faster but having more leakage current. Again, there is a matter of trade-off. Okay, so and our main objective is to reduce the delays in the critical paths, and by using this we can able to reduce the static power. Okay, dual VTH partition. We have to partitioning the threshold, or we have to partition the transistors into low voltage transistors and low threshold voltage transistors and high threshold voltage transistors. So again there is a matter of the but leakage current has more. So finally it can able to reduce the delay of critical paths, and finally it can it can try to keep the static power consumption. This is another technique to reduce the static power. And next one is variable threshold transistors. Okay, here we can adjust the threshold voltage of the transistors at runtime to meet the performance and power requirements. So reducing the VTH increases the subthreshold leakage current exponentially, and reducing the VTH also decreases the gate delay. So variable threshold transistors. So it is the one method to reduce the leakage power. So if we can increase the threshold voltage, we can able to reduce the static power or leakage power. Leakage power will be reduced. Okay, it is a technique involved in variable threshold transistors. If we can reduce the VTH means it increase the leakage current, so that we have to increase the threshold voltage. Then only leakage current can be minimized. So see this graph. So it is simple NMOS inverter having input V in, and here it is V out, and it is an VSB, source to bulk potential of PMOS and source to bulk or body potential of NMOS. If we can see this, there is a relation between VTH and VSB. Okay, VTH and VSB, there is a relation. So if you can see, if the threshold voltage changes, VSB also changes. So that what we have to do? We have to increase the threshold voltage, so that we can able to reduce this static power dissipation. If we can decrease means we have, so again static power dissipation will increase. So remember this. There is a relation between VTH and VSB. Okay. So adjusting the substrate bias at runtime is called as adaptive body biasing or dynamic threshold scaling. Okay, it is a second. It is another kind of mechanism to reduce this static power dissipation. Okay, third technique I think. So and another one is power gating. We have completed the clock gating. Now we have to see what is power gating. So, or what is empty CMOS? It is also called as empty CMOS approach. Multiple threshold complementary metal oxide semiconductor. Multiple threshold CMOS approach. And if you can see here, it is a power gating. We have to use the sleep transistors. So there are two supply voltages, VDD and ground. So along with this, we have some auxiliary voltages, VDDV and VSSV. We can consider ground. We can be considered as VSSV. These two are auxiliary voltages. VDD and ground are the supply voltage. It is a ground. VDD and VSS, and VDDV and ground V are VSSV are ground V or VSSV. These are auxiliary voltages, and these two are load capacitances respectively. And this Q1 and Q2 are sleeve transistors. Okay, it is a PMOS and it is an NMOS. It is these two are sleeve transistors. So see this operation of power gating technique. If sleeve transistor, if SL is 0, so if SL is 0, it is a PMOS transistor. No, it will be in on condition. Okay, it will be in on condition, and Q2 also will be in on condition. Why? Because SL bar is 1, right? So SL bar is 1. So 1 means the NMOS will be in on condition. So that low VTH, less delay, it is in active mode. So it will works in two modes, active mode and sleep mode. If SL is 0, so SL bar is 1, it works in active mode. So if SL is 1, so see here, if SL is 1, PMOS will be in off condition this time, and SL bar is 0, and NMOS will be in also in off condition. So in off condition, there is a high threshold voltage and low leakage, and it will works in sleep mode. Okay, by using these two sleep transistor, we can able to work this particular circuit will works in two modes, such as active mode and sleep mode. So in this, in active mode it consumes the power. In sleep mode it does not consume any power. So in this way we can able to reduce the power dissipation. It is another technique. It consumes the power or only in active mode. In sleep mode it don't consume any type of the power. So it don't consume any type of the power, so that we can able to reduce the power dissipation. So it is another technique so to reduce the power dissipation. So all these are the various techniques to reduce the power. Okay, thank you.